In this video, I will be working through last year's Physical Sciences Term 1 KZN past paper. And you know that question 1 always starts off with multiple choice. Multiple choice is a good way of testing you to see if you have an overall general understanding of your content. So here we go. 1.1 says, in which one of the following media will sound travel the fastest? Now, here's the thing. Sound travels the fastest in solids. So if we look at our options, we have air, water, steel, and a vacuum. So the answer here should be steel. Now, 1.2 says, a sound produces the wave pattern below. So here's what we've got. And it says in which diagram represents the sound wave at a higher pitch but the same loudness. So what we ask ourselves is, what affects pitch? It's frequency. Frequency affects pitch. So the higher the frequency, the higher the pitch. Now, if we look at the options that we have, firstly, understanding the transverse wave that was given to you. If we look at this, we notice that we've got 1. So here's 1 wave, 2. We've got 2 waves given. Now, if we're expecting this sound wave to have a higher pitch, we're expecting it to have a higher frequency, meaning that there should be more waves. So if we look at A appears to have a higher amplitude, but it's still 2 waves. B now has 1, 2, 3. So B looks like it could be the answer at the moment. Let's look at C. C has 1.5 waves. D has 1, 2, 3. But the problem with D is that the amplitude has been increased. Based on what they said to us, it just has a higher pitch. Nothing about amplitude has been changed. Remember, amplitude has to do with loudness. If they said that the loudness increased, then we know that the amplitude would increase. But nothing happened to the loudness. It was just the pitch that went higher. So the frequency should only increase, not the amplitude, meaning that our answer is B. So the amplitude here matches what was given to us, but the frequency is higher, meaning that there is a higher pitch. 1.3 says, which graph represents the relationship between the frequency and energy of a photon? Now, this is testing you on electromagnetic radiation. And what we learned there is that the higher the frequency of the photon, the higher the energy. If you think of your electromagnetic spectrum, where we start off from radio waves, we go on to microwaves, and then we increase all the way up until gamma rays. What we notice is that from left to right, frequency increases. And what happens when frequency increases? Energy increases. So here's the thing, right? If frequency increasing causes energy to increase, we are expecting to have a directly proportional relationship. And what is representing that here is graph C. Here, as frequency increases, energy increases. 1.4, which one of the following is equivalent to 1 ampere? So ampere is the unit of measure for current. And if you think about your formula, I is equal to Q over delta T. This formula is basically the definition of current. We know that current is the rate of the flow of charge. So, or current is the amount of charge passing through a certain point in 1 second. So here's the thing. If we have 1 ampere, that basically tells us that we have 1 coulomb. And that 1 coulomb is moving past a certain point in 1 second. So charge has a unit of coulombs, time has a unit of seconds. But if we create a unit out of this, because time is at the bottom, what happens when we take this unit to the top to go next to C? Its exponent now becomes -1. Because remember, At the bottom, the exponent of s is 1. So think of this in terms of a variable. Think of it as being x in your algebra. And according to laws of exponents, if you're going to take that x and you're now going to put it in the numerator, its exponent is going to become negative, right? So we have coulombs per second. So this is going to, 1 ampere is going to represent 1 coulomb per second. So the correct answer here is A. Now we have 1.5, which says, which one of the following cannot be the charge of an object? So this question is testing you on electrostatics, particularly the quantization of charge. And we know that the quantization of charge states that all charges in the universe consist of an integer multiple of the charge on a single electron. So the question is, what is a charge, or what is the charge of a single electron? That's going to help us get to the answer. So here's the charge of a single electron. It is 1.6 times 10 to the minus 19 coulombs. Now, the quantization of charge says that every charge in the universe consists of an integer multiple of this charge. Meaning that if we take this and we start multiplying it by integers, we will get charges of everything else in the universe. So let's start multiplying it to see what we get. And also understand that your question says which one of the following cannot be the charge of an object. So let's start multiplying, and all of the values that we multiply and we get, those will not be the answer, because we are looking for a value that is not going to be an integer multiple of this. So if we take this value and say we multiply it by 2, that would give you 3.2 times 10 to the minus 19, which we do have here as an option, okay? So that's not going to be the answer, but I'm just taking it to say that yes, that is a value that we do get. Now let's take this value, the charge of an electron, and multiply by 3. That gives us 4.8 times 10 to the minus 19, but we don't have that as an option, so that's fine. Then we're going to multiply it by 4, and we get 6.4 times 10 to the minus 19. Now let's multiply by 5. We get 8 times 10 to the minus 19. If we go on to 6, we have 9.6, and as we multiply by bigger integers, we get bigger values. So the only one here that we do not get is 7.2 times 10 to the minus 19, which means that that value cannot be the charge of an object, because it is not an integer multiple of the charge on a single electron. Now we're on to question 2. It says two transverse pulses A and B approach a point P in the same medium. The pulse B is traveling to the left and has an amplitude of 3 times larger than that of pulse A. Both pulses have a wavelength of 5 centimeters. The pulses experience destructive interference at point P, where they form a trough with an amplitude of 6 centimeters. So quite a bit of information given here. We are working with 2 different transverse pulses, and we know that when they meet in the center and when superposition occurs, they are causing a destructive interference. So that's quite important. Now 2.1 says, name and state the principle used to determine the resultant amplitude the pulse formed at point P. So yes, when they met at the middle in point P, that is known as superposition. So they want us to name it and state it. So here's what it is. The principle of superposition. It is the sum of 2 or more pulses that occupy the same space at the same time. That is 1 mark for stating the principle of superposition, and 1 mark for giving for naming it, and for stating the principle itself is 2 marks. So that gets you the 3 marks. 2.2 says, determine the amplitude of pulse B before it reaches point P. Now, if we just refer back to the information that was given, they didn't actually give you the amplitudes of the pulses initially, but they said that pulse B is traveling to the left and has an amplitude 3 times larger than that of pulse A. Now, we don't know what pulse A is either, but whatever it is, pulse B is 3 times larger than that. Since this is an unknown, let the pulse of pulse A, or let the amplitude, of pulse A be represented by X.